before I get going with the talk, I sort of feel like I need to teach you a word in English that I'm going to use quite a bit. And I think most people know the word now, but maybe somebody doesn't. So I'm from the United States. I actually came from the southern part of the United States, and we have a word there that we use a lot. It's y'all. Have y'all seen y'all? It's a contraction for you all. So when I'm talking to y'all, I'm going to say y'all. Now in the North, they would say you all, but people where I'm from have trouble pronouncing two vowel sounds in a row. So I can say you all, but did you hear there was a little pause? It's not very natural. So I won't even try to not use it, and we'll get going. Oh, and I guess one other interesting thing about the South where I grew up is usually when you go across the world, people don't really know where you're from. And the specific little town that I'm from, you all will not have heard of, but close by there's a big city, and it's big enough to where it has a basketball team. And there's actually a Slovenian on this basketball team, Luka Doncic. So I'm from outside of Dallas, and you'll be happy to know that everybody in Dallas knows about Slovenia. First from Melania, they got a little bit of a hint of it, but when Luka showed up, everyone asks about Slovenia. We know all about it. And apparently there's quite a few Slovenians who show up at games sometime in Dallas. Okay, so I'm going to talk about when are two graphs really the same. The first thing that I'm going to do is tell you about what a graph is. This is going to be a very informal talk, so I'm not going to give you the formal definition. But basically, it's just, it consists of two things. We have dots, which we like to call vertices, and then there are lines between these dots that we'll call edges. Let me give you some examples. So here's a very simple example. It's got 4 vertices. 1, 2, 3, 4. It's got 4 edges as well. Now, one thing, I made this example deliberately simple to make the point that the dots are always big dots. I'm sorry, the vertices are always very large. The lines between them are always thin. And as opposed to, say, this place right in the middle, where these two edges cross, that is not a vertex. It's just a place where 2 edges cross. Now, there's also a more formal definition. I don't really want to do it because it's sort of very mathy. But one thing I want to emphasize about it is that the formal definition, all it talks about are the dots, the vertices, and then whether or not 2 dots have an edge between them. There's no other information there. So for example, it doesn't tell you how to draw a graph. It doesn't tell you if the edges are supposed to be straight or curved, or it doesn't even say that there is a drawing. It's just dots and lines between in a mathy way. All right, this is a famous graph. We'll see it later. It's called the Peterson graph. Somehow or another, this is probably the most famous graph. It even has an entire book written about the properties it has. It's got 10 vertices. There's 5 on the sort of the outside of the graph, and then there's 5 on the inside. If you look at the number of edges, we've got 5 edges on the outside, 5 on the inside, and then 5 joining the outside to the inside. So we have 10 vertices, 15 edges. Now, sometimes it's going to be convenient for us to label the graph. So I've just labeled the graph, the Peterson graph here in a very naive way. Just 1, 2, 3, 4, 5 on the outside, 6, 7, 8, 9, 10 on the inside. In the formal definition of a graph, each vertex gets a name or a label. Now, if you look at the graph I had before, I didn't write the labels. And that's because if you look at this picture, it's a bit more crowded and cluttered. So unless I need the labels, I'm not going to write them. but if I need them, they are lurking there in the background. Here's a few other graphs. I like these. This is the octahedron here, the icosahedron, and the dodecahedron. Does anybody play Dungeons and Dragons? No? Well, if you did, Dungeons and Dragons has 5 sets of dice, or 5 die, one for each of the so-called platonic solids. And these are sort of obtained from the 3 largest ones. The smallest one, there's the tetrahedron. It's a 4-sided die, and the die everyone is familiar with is the 6-sided die. And so there's a picture of the 6-sided die. And if you view this sort of as a 3-dimensional object, where I place the vertices, these are sort of the points on the corners of the die. And we just have the 2 vertices have an edge between them if there's actually sort of a physical line there on the edge of the cube. And so these are sort of the graphs that you get from the larger ones, which if you play Dungeons and Dragons, you would know. Okay. The definition, as I've mentioned, of a graph does not specify how a graph should be drawn or any information about what a line looks like. So here, what I've got for you is 2 sort of, in some sense, identical drawings of the same graph. And all I did going from this one to this one, of course, was just take this corner vertex and sort of pull it down to the left, just to illustrate that, okay, it doesn't matter how I draw it. I could even make the lines curvy, and I even went ahead and colored some of them, which we will see later. This, if you color them, it makes it very easy to tell, to see certain properties, as we'll see. Okay. So we can draw an edge in any shape, length, or color. Doesn't do a thing. Now, if you wanted to, you could even put a little sine wave for your edge. From my point of view, that's sort of silly. But if you were an electrical engineer, this would not be a silly thing at all. I think they do that to show something or another. So if there was some reason you needed to illustrate a concept by making your graph, making the edges a different shape, you certainly could do that. Okay, so if you look back at what we've done, there's a couple of ways that we could make graphs, the same graph, look different. And that's by, say, drawing it in a strange way or a different way. And we could also change the labels. And none of those 2 things, either redrawing the graph in a different way or changing the label, it doesn't really change the graph at all. Now, with this problem of when are 2 graphs the same, there's actually 2 fundamental ways one can think about the problem. There's sort of, well, I call it the first way. This is what we're going to spend our time on, and this is what humans would do. So if you were sitting at home and you had 2 graphs and you wanted to know, are they isomorphic? How would you do it? That's what we'll focus our time on. But if your graph gets too large, there's too many vertices, too many edges, it's almost impossible for a human, quite frankly, to even draw a graph with, say, 3,000 vertices, if you like. So we also need algorithms or computer programs that would be able to tell us when 2 graphs are isomorphic. We're going to focus on the first aspect of this. How would a human do it? And I will briefly talk about how a computer would do it at the end. Although I have to say that when we talk about the algorithms, I'm not really going to give you any details of how the algorithm works. It turns out, as my colleague Russ Woodruff likes to say, it's complicated. So a bit about the language. We'll say 2 graphs that are really the same are isomorphic. This word is not English, it's Greek. The prefix iso means that the same, and morph means form or shape. So different forms, but the same. And I guess more people my age are familiar with, have y'all heard of the Mighty Morphin Power Rangers? it's the same morph as them. I never liked them, I have to say. Okay, if you're trying at home to tell if two graphs are really the same, what one looks for are differences in the graphs, if the graphs are really different or not isomorphic. Or if you think the graphs are isomorphic, you might look for similar features, or I'm going to call them structural properties. Now, there's an obvious question. If I'm going to call these things structural properties, what does that mean? Well, I've written something that basically means the same as they're isomorphic. That it's something that doesn't change no matter how you draw the graph or label it or color it or whatever. So it's a feature of a graph that is immutable. It always has it. Now, the difference between a structural property and the two graphs being the same or isomorphic is in that when you talk about a structural property, you're really talking about a feature of the graph or some information about the graph, or even maybe a little piece of the graph. So when I talk about structural properties, I'm not talking about the whole graph. I'm talking about properties that the graph possesses or little pieces. Okay, I'm going to give some examples. We're going to start with the easiest things, and hopefully these are going to be obvious to you, and then we'll look at things that are not so obvious. Now, the first things that we're going to start with, they don't tell you anything about when two graphs are isomorphic. We're going to get two easy sort of tests to see if graphs are not isomorphic. So the easiest way to tell if two graphs are not isomorphic is if they have different numbers of vertices or edges. Because what? If you think about redrawing a graph, that's not going to change the number of edges you have or the number of vertices. And so these two graphs are not isomorphic, and hopefully I've made it obvious that what the graph on the right, this one here, it's got one more vertex and one more edge. Now, I deliberately drew the rest of the graphs to be identical because you just have to be off by one for the graphs to be different. They can be very, very, very close to being the same, but any different, and the answer is they're not isomorphic. Okay, how many pieces is the graph made of? What do I mean here? Hopefully this is going to be obvious. So this thing on the left-hand side is one graph. It's got two pieces. You can see there's that top triangle and this bottom triangle. Oops. The graph on the right is one piece, and I sort of drew this deliberately so that you could see that all I did going from the one on the right to the left is sort of split it apart. Or if you prefer to look at the one on the left, you can get the one on the right by joining them together. So these are very similar graphs, but they have two different pieces, two pieces on the left, one piece on the right, so they are not isomorphic either. I'm going to just make the obvious point. The one on the left has 6 vertices and 6 edges. The one on the right has 5 vertices and 6 edges. So we could tell that these two graphs were not isomorphic in 2 different ways. And I wanted to point that out because usually when you're thinking about isomorphism, there isn't going to be an answer like a solution to an equation. There's usually going to be many justifications that can be used. Okay. I have to give you a definition or two before I get to the next property. So the first one is a cycle. And here I'm going to give you sort of the mathy definition, so at least you can see one. So it's going to be a sequence of vertices, and I'm just going to call them V sub 1, V sub 2, up to V sub R, and then V sub 1. So the first vertex and the last vertex are the same, but all the other vertices, V2 through VR, are all different and all different from V1. The second feature is that if you look at successive vertices in this sequence, V1 V2, that's going to tell us if it's a cycle that the edge V1, V2 is an edge of the graph. And then V2, there's an edge from V2 to V3, an edge from V3 to V4. And then finally at the end, there's going to be an edge between the VR and V1. Usually these cycles are called R cycles, and notice that the R is right there. Let me give you some examples, and I think this will sort of clear it all up. So on the left, I have a 3 cycle. So you might think of this top vertex as being V1, V2, V3, V1. The next one over is a 5 cycle. We also call that a pentagon, sort of in the obvious way. So V1, V2, V3, V4, V5. And here's a 6 cycle, which we will call a hexagon as well. Oh, so did y'all see that? The middle graph changed. 5 cycles can be drawn in a nice symmetric way in 2 different ways. So the first one, we just go around the cycle, but the second one, if you start at the top, we go V1, V2, V3, V4, V5, V1. With triangles and hexagons, there isn't another nice symmetric way, but of course there's lots of unsymmetric ways. I sort of left out the 4 cycle, and if you're thinking about a 4 cycle, what the corresponding geometric shape would be a square, but for some reason, and I don't understand why, we don't call a 4 cycle a square. We call it a 4 cycle. I don't know why. Right. Okay, so that's the first definition. Second definition, we're going to see some similar weirdness in terminology. We need to talk about the valency of a vertex. It's just the number of edges at a vertex. So here's this is a famous graph. This was actually the first graph in history. We actually know what the first graph was. It was in a paper by Leonard Euler in 1736, and this is called I didn't write the title here, but it's called the 7 Bridges of Königsberg graph. So you can look that up on the internet, and it will tell you all about it. But let's count the valencies. Here I labeled the vertices so that I could talk about them individually. I have to say, I find the labeling a little weird. We read from left to right and top to bottom. So if it were me, I would put an A there and probably a B there, a C there, and a D there. But I'm using the same labeling as Euler used, just because. All right, so what about the valencies? Let's start with C. There's 1, 2, 3 edges there. With D, there's 1, 2, 3 edges there. With B, there's 1, 2, 3 edges there. With A, it's a little different. There's 1, 2, 3, 4, 5 edges there. Okay. Now, if you think about the valency, if you move a vertex around in your drawing, if you relabel it, that's not going to change the number of edges at that vertex. Now, when we're talking about, valency, y'all had chemistry? There's valency in chemistry. It's the number of electrons available to bond with other molecules. And if you are thinking of these models, there's one, water, and that looks exactly like a graph. And you can see from the picture that hydrogen has 1 electron available to bond, oxygen has 2. So if you were wondering about why anybody cares about graphs, there are actual chemical properties of molecules that are completely determined by the graph-theoretic structure of this drawing of the molecules. And there's actually, it's called chemical graph theory, go figure. And there's actually people here at the University of Primorska who do this. And in the former Yugoslavia, there's quite a few people in Croatia and in Serbia who work on this sort of chemical graph theory. Now, the reason I'm saying all this is you can see that valency it's sort of a natural term, but down here, I'm going to talk about degree sequence. And it turns out that degree and valency are synonyms, but let's look at the two graphs that we have here, and let's see what their valencies are. Now, this one, it's got a vertex of valency 3 here, 2 there, 3 there, 2 there, 2, 3, 2, and 3. And so if you list them, typically, you want to list them from largest to smallest or smallest to largest. And I think when I was a student, we were supposed to list them from smallest to largest, but if you go to Wikipedia, you're supposed to list them from largest to smallest. And of course, it doesn't matter at all. You just want to put it into a form that's easy to compare. This graph on the right, it's got valency 2 at that vertex, 2 at that vertex, 2 at that vertex, 2 at that vertex, 3 there, 3 there, 3 there, and 3 there. And so if you look at this sequence, 4 2s and 4 3s, 4 2s and 4 3s. So we've seen that the labeling, if you redraw a graph, that the valencies don't change. So if you have isomorphic graphs, these sequences must be the same. And if they're different, you'll know that the graphs are not isomorphic. But here we have two graphs with the same degree sequences. And what do you think? Are these guys, they look isomorphic? It turns out they're not isomorphic, and maybe this is the smallest example. For me, the easiest way to see this is to focus on the vertices of degree 3. If you look at the right-hand side, you'll see that those 4 vertices of valency 3, they're a 4 cycle. And on the right-hand side, they're not. They're not really much of anything. It's just sort of almost a straight line. And if you stop and think about a structural property, what about having a 4 cycle? Well, if you redraw it, you're still going to have a 4 cycle. If you relabel it, you're still going to have a 4 cycle. So these graphs are actually not isomorphic because all the vertices of valency 3 are in a 4 cycle on the right-hand side, and that's not the case on the left-hand side. Okay. And yeah, if the lists are the same, they might be isomorphic. Okay. This sort of ends the first part of the talk, where the emphasis was on, let's understand what a graph is, what it means for two graphs to be the same, and these simple tests to see if two graphs are not isomorphic. So going forward, none of those tests are going to work. We're going to sort of consider that to be boring or easy. And in practice, it turns out that focusing on cycles is a pretty effective way of deciding isomorphism. It doesn't work all the time, but there are many, many examples in the literature where people will show that two graphs are not isomorphic because one has a 5 cycle and the other one doesn't, or even that one of them has a bunch of 12 cycles, but let me go 8 because I know a result in the literature that uses 8. They have different number of 8 cycles through a vertex. And if you think about the number of 8 cycles that go through a vertex, however you redraw it, those 8 cycles are still going to be there. So that's also a structural property. Now, when you're picking cycles, probably my initial comment about 12 is probably not very good. When you're looking at cycles, what you probably want to do is not focus on things that are terribly small, like triangles, typically, because if you have a relatively complicated graph, there might be a lot of triangles. If you have a lot of triangles, this is not so good. You also don't want to look at large things, because large things can be hard to find or hard to find all of them. So in some sense, we want the Goldilocks, the three bears. We don't want our porridge to be too hot. We don't want it to be too cold. We want it to be sort of just right. Now, if your graph doesn't have 12 cycles, suppose it only has 3 cycles and 4 cycles, then what's large and what's small? Well, everything is okay there. And similarly, if you had, say, 4 cycles and 6 cycles. So typically you don't want really long cycles, but if all your long cycles are short, yeah, you should look at all of them. All right. What I'd like to do now is I'm going to give you a pair of graphs. So this is a graph on the left here, and this is a graph on the right. And what I'm going to do is I'm just going to have a painfully awkward pause and let y'all stare at these and decide if these two graphs are isomorphic. And then once you've had a chance to think about it, I will come back and tell you what I think. And so I'll start the painfully awkward pause. So I gave an extended version of this talk to some high school students here in Coper earlier today, and it was very easy for me to tell when I should end the awkward pause, because they'd be whispering to each other. So I'll just give it a minute or two. So what do you think? Isomorphic or not isomorphic? Are they the same or are they different? For me, the thing that I have to say, this graph here, it's actually one of my favorite graphs. It's not a very fancy graph, but I really like it because those triangles they just jump out at me. And that's what I'm going to focus on. And so what I've done is on the left, I've highlighted these two triangles in red to let you know that I'm going to focus on them. And if you look at the graph on the right, it has two triangles as well. This one here and that one there. This morning, when I asked the high schoolers if these were isomorphic, a young lady gave me a very nice sort of graphical, and I mean graphical in the picture it in your mind way, not graph. And she said, oh, if you look at this, we've got these two triangles, and if you sort of take maybe this triangle and pull it this way, and take the other one and pull it that way, and then rotate, you'll get the same graph. And that's absolutely correct. And I have to say, I knew about that, but for me, this is not terribly natural. I guess I don't see things geometrically very well. One of the reasons I'm telling you this is to let you know that there's more than one way of thinking about these. Now, once I had my two triangles that I like, what I did was I labeled the graphs. And maybe I should have broken this slide into 3 or 4 slides, but let me just tell you that I labeled this graph first. And I just sort of did it in the obvious way. 1, 2, 3, 4, 5, 6. It seems to yell to me that, label me. And so I did. And then what I did was I looked at my 2 triangles. They're labeled 1, 3, 5 and 2, 6, 4. And so I labeled them 1, 3, 5 and 2, 6, 4. Now, I also have to say that the first time I labeled them like that, the young lady's twist was not taken into account. So the first time I did this, it didn't work, but then here it will. So because I've labeled the triangles the same, I know that the edges on the left-hand side and the right-hand side inside the triangles are edges of both graphs. So if you're thinking, oh, what other edges do I have to check? For me, these are easiest to see on the left-hand side, the edges between the 2 triangles, and they're labeled 3, 6, which is this edge here, and then 1, 4, which is that one there, and then 2, 5, which is that one there. And because what? If you look at the number of edges in total, there are 9. These labelings show you that these 2 graphs are really the same. Yes, they are. All right. Here's our next pair. And again, we'll have the awkward silence for a minute or 2. Okay, what do you think? Isomorphic or not isomorphic? I had a head nodding yes. And that's correct. They are. And what did I start to think about this time? For me, the left-hand graph was the one that really jumped out at me. It's got a cycle that contains 6 edges. It contains all the vertices. So what I did was I started to look for such a cycle in the right-hand side. And the way I did this is sort of going to give you an idea of how complicated my brain is. I just started at the top and, oh, there's an edge. And then I can go down and over, then back, down and over, back, and then I can get back to the start. So there was the 6th cycle that I found. And again, I just like to go left to right, top to bottom, because that's the way we read. Then I decided to label them just like I did last time, except this time, oops, sorry, I paused and yes, I'm supposed to point it there. Oops. Yeah, this time, I actually started not with the one on the right, with one on the left, where I knew that there was this nice natural 6th cycle. And normally, given my brain, I would start right there with 1. But this time I wanted to deliberately start somewhere else to let you know that, okay, it doesn't really matter. It's a cycle. You can start it anywhere you like. And so I labeled it 1, 2, 3, 4, 5, 6. And then, of course, on the left-hand side, I did sort of the order that I found the 6th cycle in. So 1, 2, 3, 4, 5, 6, and then back to 1. And again, there's only 3 edges that I don't know are correct because every other edge is in a 6 cycle. And to me, they're easiest to see on this side. So we've got 1, 4, and that's 1, 4. We'll check 2, 5, and there's 2, 5, and we'll check 3, 6, which is 3, 6. So these two graphs are isomorphic. Okay, let's go to our last one. This one's a little bit, depends on how you look at it. It's easier or harder. So I will pause maybe a little bit longer for this. Okay, so what do you think? Ah, I missed that. Shows you how great I am with Zoom. Ooh. Good. That's the easy way. Left one doesn't have a 4 cycle. The one, so yes, that's correct. The one on the right, it has this obvious, well, I guess obvious 4 cycle. And if you go on the left, you won't find one. And it's sort of interesting because if you're a graph theorist, you can't just say, well, I looked at it and it doesn't have one. You have to, because that's just not, I don't know, that's not educated enough. So there's actually a phrase that people use to say, I looked at it, it doesn't have one. It's by inspection. The one on the left doesn't have a 4 cycle. Now, another thing that you might have done, and this is, I don't know, to me, this is a little bit more complicated, but for me, these cycles really jump out. And if you look at this graph, remember that's the Peterson graph, it's got a 5 cycle on the outside, it's got a 5 cycle on the inside. And if you look at this graph, it's got a 5 cycle on the outside and a 5 cycle on the inside. So in some sense, this game I was playing before, it looks like it's going well. But a different problem, other than no 4 cycle on the left, is that the graph on the right only has those 2 5 cycles that we saw. And you can see this very easily because what? If it's not this outside 5 cycle or the inside, if I start on the outside, well, if I come over here, I get the 4 cycle. So if I go further, well, I'm going to get a 6 cycle. So there's no way to get a 5 cycle there. One thing that might also help you is it clear that there's some symmetry here, that both of these graphs, I can just take them and I can rotate them 5 times and I get back to where I started from. The graph on the right, it's also easy to see that somehow I can swap the inside and the outside, and that's not going to change anything. With the Peterson graph, you can do that as well, but it's a little more complicated. So this graph on the right only has 2 5 cycles. The Peterson graph has many. Maybe I turned it off. So here we focus on. Now it'll work. Okay, thank you. So they both have the obvious 5 cycles. I've done those in red. Let me show you some more 5 cycles on the left-hand side. And so the right-hand side stayed the same. The left-hand side, I've now given these new 5 cycles in blue, and you can check that, yeah, okay, here's one. That's a 5 cycle. And then there's one here. It's also a 5 cycle. Now, if you wanted to, you could now find 8 more 5 cycles by taking these 2 and rotating them 5 times. Since we have 2 to start with, that will actually give you a total of 12. And by inspection, that's the total number of 5 cycles in the Peterson graph. So these graphs are not isomorphic. Okay. Let's now talk about sort of the end. Let's go back to the computer algorithms that I mentioned earlier. But if you look back on our examples, we looked for distinguishing features. And if you think about a graph, it may have lots of distinguishing features, but it may be, as with these graphs, that there's a lot of symmetry. And somehow you can't tell any vertex from any other vertex unless you just put a label on. So for example, in this graph, I really can't tell the difference between this vertex and that vertex other than just by where their position is, because I can just rotate the picture clockwise and that vertex will become that vertex and the picture stays the same. So my intuition says that these sorts of graphs are going to be hard to tell if they're isomorphic, because if you're looking for a distinguishing feature inside a graph, in some sense, they don't have any. Everything is, the viewpoint is the same. Such graphs are called vertex transitive, and I wanted to mention that because there's a very large group here at the University of Pomorska studying these graphs. And this intuition is correct. There's a guy named Eugene Lux. He's now a emeritus professor at the University of Oregon, but in 1982, he showed that the isomorphism problem can be solved quickly if it can be solved quickly for vertex transitive graphs. This was not a terribly long paper. It was 24 pages. Yeah. The other reason I'm mentioning this is that in 2015, Laszlo Bajbaj, who's originally Hungarian, but he's now at the University of Chicago, he used the exact framework that Lux developed in 1982, and he didn't show that there was a fast algorithm, but he showed that it wasn't really slow, and it was sort of in the middle. Technically, what he showed is the problem can be solved in quasi-polynomial time. Now, what does that mean? Okay, and what's good and what's bad? So computer scientists say good is if there's some polynomial, a polynomial, in the number of vertices, and if you plug the number of vertices in, this will tell you how many steps the computer must take in the worst case to figure out if the 2 graphs are isomorphic. Okay, so there's one polynomial that works for everything. Bad is exponential number of steps, and we all know that exponential functions grow very quickly. What does quasi-polynomial time mean? Well, it means that if you look at the worst case number of operations that the computer would have to take to determine isomorphism, it is a polynomial in the number of vertices. But if the number of vertices gets bigger, the polynomial need not stay the same. The degree might go up. Does it make sense? So polynomial is good. There is a polynomial for fixed n, but as the number of vertices goes up, the degree of the polynomial may go up. Okay. And it's not known if the problem can be solved quickly in polynomial. So one thing that I find very entertaining about this is when I was a young man, I met Bye-Bye, and he was not at the University of Chicago, and he was a mathematician. And if this was a very famous result of Bye-Bye's, it was written up in the scientific media, not just in journals. And in all of these news reports, they would talk about how this was the most important problem in theoretical computer science. And Bye-Bye is not in the math department at the University of Chicago. He's in the theoretical computer science. One thing that this sort of shows you is the overlap between graph theory and this other field, theoretical computer science. And many young people who are interested in math are also interested in computing. And what this sort of shows is that, well, if you wanted to, you could study computer science and switch to math, or probably if you're interested in both, a better option would be to study math and then switch to computer science. And I'm not actually making this up. My daughter did an undergraduate degree in math, and now she's doing a PhD in theoretical computer science. Her fiance is also doing a PhD in theoretical computer science, and sort of the basic foundations of his research are results that my supervisor proved 20 or 30 years ago. My supervisor is not a computer scientist. And also this morning, when I was giving a version of this talk to the high school students, the teacher came up to me after the talk and said that her daughter started out in math and then switched to computer science. So if you're a young person thinking about what to study in college and you're thinking math or computer science, you don't really have to choose as a high school student. You can wait and make that decision later. Okay, I think that's all I have, except it's traditional. Oh, I'm sorry. I forgot one last thing. Practical things. If you really wanted to ask the computer, the best program at the time right now is by a guy named Brendan Kai. He's currently at the Australian National University, and it's called Naughty. It's really not naughty, but there you go. What was I going to say? Oh, one other thing, if you're a young person, about all of these people, is that if you think about the people you've seen in math, you might have heard of Euler. He was the guy who did the 7 bridges of Königsberg, and he's what you call dead. And if you take calculus, you'll see Leibniz and Newton, the inventors of calculus, and they're dead too. And most of the mathematicians you'll see as a young person are not just dead, but they're really dead. They're not even close to being alive. And I find it very nice for students when you get to the frontier is when you hear about people who weren't dead. All right, that I think is the end, and it is traditional for me to thank you.